Thank you, Luna, for the presentation, and to the organizers for the opportunity to speak here. It's my first time in France, so thank you. Okay, so today I'm going to talk about a recent work in progress with Michael Jampolsky, and it's about bicubic circle map. Okay, so first I'm going to define what the map that I'm interested in. So real analytic unicritical circle maps are just analytic orientation preserving circle homeomorphisms with a single not degenerate critical point. The usual criticality of that critical point is 3. Okay. So there is a very famous theorem by Jocose, the 80s. He proved that these maps are topologically conjugate with the corresponding rotation. So topological, these maps are rotations, irrational rotations, of course. So in particular, if you have two real analytic unicritical circle maps, they are topologically conjugated if they have the same irrational rotation. Okay. Okay, so that renormalization theory that Misha talked this morning has been very well developed for this kind of maps, so maps with only one critical point. So there is more or less a list of results. So there is a horseshoe attractor for renormalization for this map, for in the case of irrational rotation numbers. There also a Banach manifold where the attractor is hyperbolic with a single unstable direction. And these real analytic unicritical maps with the same irrational rotation number, they form an unstable manifold of the horseshoe. Then it's possible to prove the topological conjugacy given by the Jocose theorem to a smooth one. This is what we call rigidity. Okay. So this is done for one critical point, cubic, one critical point. And the question is, well, what happens when you add more critical points? Okay, so in this talk, we are interested in bicubic circle map. So real analytic circle map with two non-degenerate cubic critical points. And of course, we are assuming all the time that we are in the case of irrational rotation number. So the theorem of Jocose is still valid in this case. Is valid for finding number of critical points. Okay, so there is an example, a very nice example given by Zachary. So I call that Zachary's map. So it's a 3-parameter family. So P and Q are complex numbers with modulus bigger than 1, and T is a number between 0 and 1. So Zachary's map is given by this formula. Only formula that I will show in this talk. And the theorem, well, Zachary proved a lot of things, but one of these results is that if you give me an irrational rotation number and a number delta between 0 and 1, so there is a unique map of this type, of this type 1, or a Zachary map, such that the map restricted to the circle is bicubic, the rotation number is the number that you gave me, and more or less, if you consider the arc between the two critical points, and you measure but this mu v, which is the unique invariant Bay invariant measure, the measure of this arc is delta, the number that you gave. Okay. So another result that Zachary proved, I think this was in his PhD thesis, is that if you have a Blanchet product with two critical points in the circle, then that Blanchet product should be a composition of a map in this Zachary family with a rotation. So so this is a very nice examples of cubic maps. Okay. So now I'm going to go to the renormalization. I'm going to try to explain a little more what Misha Shishikura talked this morning. So just to recall, when you have a irrational rotation number, you associate an infinite continuous fraction expansion. So the idea here is to truncate that function. So you do the calculation and you get a sequence of fractions, Pn over Qn. So this Qn satisfies this recurrent formula. So when you know the first two numbers, you will, and of course, if you know this constant A, you will able to know all the other constants. This Q are called first iterates, or iterates of first return. Okay, so to define renormalization, I will consider a point in the circle. I will call X, and I consider these 2 points given by the iterates Qn and Qn plus 1, given by the denominators that I showed you in the last slide. So this is an interval here. I call this In, and this one is In plus 1. So this interval is smaller because this iterates Fqn, Qn plus 1, Qn plus 2 will approach to the point, will never be the point because we don't have periodic points, and they will approach in different sides. So if this comes from this side, the other will come from the other. Okay. Okay. So there are 2 iterates, one corresponding to this big interval that I will call black interval, another iterate for this small interval that I will call blue, that make that this union of interval will come back to the interval, so to this union of interval. So this blue interval, if you start to iterate, is exactly Qn minus 1 time, you will arrive in a certain place of the circle, but if you iterate one more time, so if you consider the iterate Qn, you will arrive exactly inside this union in this part, okay? And the same with the black interval. So you iterate Qn plus 1 minus 1, you will be in an interval in a part of the circle, but if you iterate one more time, you will come back to the union, exactly in the part that is missing. So in fact, all these iterates form a partition of the circle. So if you have another critical point, for example, if this X point is a critical point of your map, since the iterates of these 2 maps cover the circle, if you have another critical point, that critical point will be in an image of the blue interval or in an image of the black interval. Or equivalent, you will have an pre-image of the other critical point inside this black interval or inside this blue interval. Okay? And this is how we define renormalization. This is what we call a critical commuting pair, right? Because we have a pair of marks, and because usually we take this point exactly as a critical. So this is the formal definition. I'm not going to be more precisely, but more or less you choose a leaf of your map. You are now you are assuming that you are in a real map, so you are considered a real map, interval map, and this point will correspond to a critical point. So as I said, the union of the image of the blue and black interval, so this will correspond to the blue and this one to the black, will cover the circle. So if you have another critical point, there will be a pre-image of the other critical point inside the blue or the black. Here, this point represents exactly the other pre-image. Okay, so this is the renormalization. This is how we define renormalization. Of course, we have to choose an n, number n, and we define these 2 pairs. This pair. So of course, if you define n renormalization, you could define the other. Just you could do the same, but change n by n plus 1. or just using this renormalization that you have been constructed before, and then start to form the other. So the other is more or less simple. You consider this endpoint, and you start to iterate until you pass from positive to negative image. So in that moment, you form this blue box. Inside that box, you have this part of the map that you have before, and this one corresponds to the iterate of the old one with a certain numbers, this other old one. So the number that you iterate is exactly coincides with the next constant in the continuum fraction. So this is a sequence of renormalization. The idea is to zoom it to a defined size in such a way that you could see how the renormalization are. Yes? Okay, so this is a sequence of renormalization, and this is how renormalization is defined for circle maps, critical circle maps. Okay, so as Misha mentioned this morning, we can obtain rigidity results using this renormalization. So for some combinatoric, the exponential convergence of the renormalization, as simple as real maps, will imply rigidity. So, but this is a little difficult to prove how to prove that convergence of renormalization. So until now, this has been all real dynamics, but now here starts complex dynamics. So how can we prove the convergence of renormalization? So me should say that in this morning, the idea is to complexify the map. So I did a picture because I think it's better to understand, even for me. So you have a circle map here. This is an F circle map. You can associate a commuting pair such, using the return time. So the idea is to complexify this interval map. So this part here until here, this corresponds exactly to this interval, and this small interval here will correspond to this one. So the idea is to consider analytic extensions of these two maps here, which will be something like this. So this will be the map eta. So here we have an interval map, and here we can find a domain where eta is defined, and the same for the other part of the interval. So these two, in fact, these three, because this is a domain of the origin, these three intervals are analytic, and they go to this bigger disk. So this is the complexification for this renormalization. And of course, we need put some conditions on the combinatoric to get something like this. The picture could change if the combinatoric. So for rotation numbers unbounded, the picture is not like this. So this is corresponding to constants an in continuum fraction expansion bounded or bounded type. I'm going to explain more later. Okay, so so once you have the convergence of the renormalization, there is another part of the history that is the hyperbolicity of renormalization that I also mentioned in the case of one critical point. So this is a result of Jampolsky 2 years ago. So he proved that there exists a Banach manifold structure on the space of analytic bicubic circle map, such that, well, that structure is compatible with the topology of uniform convergence. The operator, the renormalization operator, is analytic in an open set, and if you give me a quadratic irrational number and a delta, which is the distance of critical points, there will be a bicubic with this irrational rotation and with this measure of the critical point, which is a hyperbolic periodic point of the renormalization. But in this case, the periodic point will have two unstable directions instead of one in the case of one critical point. So this is the difference between bicubic and unicritical map. Okay, so I did this picture to show how Jampolsky did that. So we have so you have your circle map, you have your pair, and under certain conditions of the rotation number, you could obtain this that I call butterflies, which is holomorphic pair. And the idea, in the case of Jampolsky, the idea is to find a Banach manifold where renormalization is a dynamical system. So you can study the hyperbolicity of that dynamical system. So what he did is a little technical. Maybe you all know more than me about this trick. But the idea is to consider, so here, so in this wing of the butterfly, the idea is to to find two points which are conjugated, a domain, a curve that join this point. This one is the image, but the map, which is the eta. And the idea is to consider this domain without this point, and the action of the pair in that domain, except these points, it's homeomorphic to the cylinder. So this is when this is how you come back to a map in the cylinder. So, so you could define. So you could define renormalization from here to here, from the space of circle map, bicubic circle map, to the space of bicubic circle maps, and it's called cylinder renormalization because you come back to a cylinder, but restrict to the circle, it was just a circle. Okay. Okay. So. Okay, so our goal is to extend that results by Polsky. So now consider bonded type rotation numbers. So bonded type rotation number is just, this is the definition. The supreme of this constant in the continuous fraction expansion is bounded by a natural number. So why we want to do that? Well, because first, quadratic irrational where the Jampolsky theorem is valid are dense in that set of bonded type rotation number. And second, because we have a theorem joined with Daniel Esmania and also Michael Jampolsky, that you have a compact set of bicubic circle maps, all of them with bonded type rotation number. So this is for any B, there is AB, such that the renormalization is invariant. And if you take any bicubic circle map with bonded type rotation number, so the renormalization of that map converges to that set AB. Okay, so we want to extend that that theory, but there is a technical thing. The first one is that use the set AB can contain unicritical circle maps of order 9. That means that the two critical points collapse. So this is not happening in the case of Polsky. So when we are in that case, we are only one critical point of order 9, the two unstable direction of the orbits will collapse into one, because this is the result for one critical point. I say that this is true for criticality 3, but in fact is more general. So for order 9 is also true. So the two unstable directions will be only one. So, and the idea is to generalize that result of Jampolsky. So we need to have the two unstable directions. So what is the thing that we are not seeing is that maybe in the unicritical case we don't see, because we only have one critical point. But for more critical points, the thing is that we need to find a functional space where that collapse collapsing is not happen. So this is called the space of pairs, of triplets, sorry. And where the space of circle maps embed. So of course we need to extend the renormalization operator, but if we are able to do that, it will be okay because we will stay with the two unstable directions. So I will say this more or less quickly, but if you are in the, so here, for example, if you, the worst case is when you have a critical point of degree 9. So for example, this map here, this delta, eta, has a critical point of degree 9, which is the worst case. You will know, that this map can decompose as the following. And this is a uniquely decomposition. This Q map is just the cubic map, so tends a point C to the power of 3. So this map that is defining the wing of the butterfly can be defined of this form. Of course, these maps should be nicely chosen because, for example, this map goes to the complex plane, but this one goes to the complex plane, to the cylinder, to the complex plane, and this one to the complex plane, from the complex plane to the cylinder, right? Because this map is will be a cylinder map. So when you, even if you have a critical map of degree 3, even of degree 9, you can find these 3 conformal maps, and they are unique. So the idea is to consider this uniformizing coordinate that I showed you before, that sends to the cylinder, and identify this eta with this triplet. So this H, it's here is the inverse, and this is the map. So this defines a triplet. So this is Phi1, Phi2, and Phi3 of the map F, and this is how we can, for a given eta, we can associate corresponding triplets. So this is 1-to-1 injective. So the space of circle maps could embed to the space of triplets. So in the space of triplets, we cannot see this collapsing because even if this cubic, we will have 3 components, right? So what we are working is exactly to show that in that space of triplets, first we need to extend the renormalization operator, and not only extend it, but extend it in a way that is analytic. We need to derivate it. So the attractor will probably go to like a leaf for the renormalization. Now defined in the triplets space, and the attractor will be uniformly hyperbolic because we preserve the 2 dimension stable point. Okay, so done. Thank you.
Thank you, Gabriela. Are there any questions or comment, live or online?
How does the arithmetic nature?
Sorry?
How does the arithmetic nature of the rotation number being a quadratic irrational come into the proof?
Yes, because if it's quadratic irrational,
what makes a quadratic irrational different from an arbitrary number of bounded type?
Yeah, because this function is periodic, this one is periodic. So it will there exists an n such that the expansion is essentially that. So renormalization will act on rotation number as a shift. So for free renormalization, for example, if I start here and then I renormalize, the rotation number will be this one. And then if I still renormalization, I will shift.
So it's the periodicity of the continued fraction that comes into it?
Yes, yes. This is the period of the renormalization.
Okay.
And just a comment, why they are starting to study this one, because it's easy to see what are the periodic points. And then, so when you know what are the periodic points, since the bonded since this set is dense in the bonded type set, so it's natural to try to extend to the that.
I actually have one more question. Can you tell us in the picture where you had a picture with two annuli drawn in a little bit further?
Yeah.
One more. Yes, here. What are those points, p plus eta and p minus eta?
So these points always exist for irrational rotation number. If your rotation number is irrational, you never have periodic points in the real line. So in that case, there always exist these 2 points. I don't remember very well, but if the rotation number is irrational, so these points are related with the non-periodic points in the real line.
Mitsu has a question.
Yeah.
Mitsu.
Can I ask a question? So what's the effect of number theoretic nature of delta? Suppose the rotation number is, say, golden mean, so it's fixed. And then when you apply this process, delta will be changing along the sequence of renormalization. So you don't have to have some boundedness condition or anything for the delta part?
Well, I don't know if I understand the question, but this delta, so the existence of the periodic points are given by this result of Zachary. So this delta, I don't know if I understand the question. This delta should be bigger than 0, right?
Yeah. So, for example, for rotation number, when you renormalize, the rotation number will be changed by a Gauss map.
Yes.
So that you are shifting the continued fraction expansion. Then at the same time, when you renormalize, the delta will be changed.
Yes.
So
yes,
you are going to get the sequence of deltas, and well, sometimes it could be very close to 0 or very far.
yes.
And are there any effect in these estimates?
So the idea is that this, okay, I think I understand the question.
Well, for the renormalization, there are always a combinatorics which is associated to it. So in the case of irrational rotation like dynamics, these are rotation numbers and the Gauss map, which shifts the coefficient of continued fractions. But if you have two numbers, you have combinatorics acting on the pair of these rotation number and delta, and I wonder what's the effect on this delta part.
Supposedly no, but I don't know how to say that. Yeah, but I don't know. I'm sorry. I don't know how. Yeah, I think I understand the question, but no, I don't know how this. Sorry.
Okay, thank you.
Dima?
Yeah, I think I have a related question probably to Mitsu's. So you have two unstable eigenvalues. Did you compute such as unstable eigenvalues for one of the examples? So I'm just wondering how different these two unstable eigenvalues. So one should correspond to the Gauss, one should correspond to the change in the rotation number, and the second eigenvalue should correspond to change in delta. And
Yes.
I would assume that the second is smaller than the first, but yeah.
Yes, what you say is true, but if I can calculate the eigenvalue,
Well, I mean, estimating, yeah,
estimate.
kind of.
No, I think
Yeah.
I think it's not.
Maybe you did some experiments, I don't know.
Yeah, but no, we
Yeah.
probably it
Okay.
could be done. Yes.
Yeah, but do you know that the second eigenvalue is smaller than the first? So is it easier to show?
Sorry, the
Oh.
second.
But do you know which eigenvalue is bigger? So do you? So I would expect that the Gaussian eigenvalue is bigger than the second, but
Yeah, that's a good question. I don't know exactly, but yes, one should be bigger than the other. I don't know if the first one, but yes, it's a good question.
okay, thank you.
Let's thank the speaker again.